Hey yo, what's up guys? Baby Bear 4812 coming at you one more time. Problem number 120 today. It's an old problem. It's called the triangle. So it's been around for a while, but in the past 0 to 6 months, Amazon, Apple, Bloomberg have all picked it up. So we're gonna pick it up today as well. The reason that I chose this one is because this one actually tripped me up. And it may trip you up if you haven't done this before, but you've done max path sum of a tree. All right, because the logic is very similar, but almost flipped on its head in a way. And so there's a really great way to do this. There's a really not great way to do this. And I, of course, did the not great way first. So basically here to teach you, like always, to not do what I do. All right, so if you haven't tried this problem, pause the video, give it a run through, and then come on back and let's try it together. So the problem says that you're given a triangle in the form of the nested array, and you need to find the minimum path sum, okay, minimum path from top to bottom. Each step you may move to adjacent numbers on the row below. For example, the given triangle right here, this little pyramid, and we see 2, 3, 5, 1. They've kind of highlighted for us as the most optimal path, most optimal meaning minimum sum. Says bonus points if you're able to do this using only O of n extra space, where n is the total number of rows in the triangle. All right, I think we'll be able to do that. All right, I think we will. So there is a O of n squared way to do this. So in terms of space, there's an O of n squared way to do this. There's an O of n way to do this. There's also an O of 1 way to do it. And I'll show you that one as well, because quite frankly, I think that's the best one to go with. And again, when you're at your interview, you'll clarify with your interviewer whether or not what you're going to do is permissible, like I always kind of advise, but we'll get there in a moment. There's also, I think, like a 2 to the power n, which is going to completely like botch out on you if you try that. Again, that's the one that this guy did. So let's jump into some logic and see how we go about thinking about this. So I've drawn it out here for you, and the reason I've kind of the reason I've drawn it out is because we want to go through it, but the actual logic behind it will basically be as follows. What I tried to do was basically to say this: at any given point, let me essentially take my value that I have right up here. So I'll start with the 2. For example, now I was doing this recursively, and I said we'll start with the 2. And then let me recursively jump down all the way to the bottom. And as I get to the bottom, at every single point, I want to check what is the sum of every combination of numbers here. So I wanted to check what is, if I'm jumping down this way, so I get all the way to the end, and these are kind of our leaf nodes. If you think, I was kind of thinking about it as a binary, or not even a binary, but like an n-ary tree. And what I was trying to do was to say, okay, well, I'm down at the 4, and so, from the 4, we don't really have any path to take. These are both non-existent, so we just have a value 4. And then I said, okay, I'll take the 6 and the 4 and kind of recursively jump in here and pick the one that's better between the 2. And then I'll do that with the 5 and the 1, and the 5 and the 8, and then the 7 and the 8, and the 8 and the 3, and so on. And then the problem is if this is kind of going to grow exponentially as you're double tapping into your own resources mainly. And this approach actually works really well with the maximum path sum problem, which if we drew something similar, and I'm sorry, I don't know why my computer's being wacky. Okay, if we had something like a simple binary tree and we had this problem, then we could actually take that approach and really at any given point, what we'd have to do is ask ourselves, what is the maximum gain that I could potentially take, or in the case of minimum path, a minimum gain, by choosing every single node. And then in each of these nodes, we would choose, well, it's another video done for you. If I'm at the node 3, I'd tell myself the best I could do is it 3 plus 5 or is it 3 plus 6, right? And we kind of build that up backwards. I'm not going to go into that because I think I've got another video that explains it. But if you try to do that over here, you're going to be in for a wild time, okay? This thing it's not going to run. You can try to implement it. If you don't believe me, you'll see it for yourself. But essentially, that's kind of where the issue lays. What maybe not as intuitive, again, especially if you know this approach, is the fact that now that we don't have a tree, we've kind of got an array, we can actually start from the bottom and go upwards, all right? And let's think about that. How would we start from the bottom and go upwards? Well, let's look at this array kind of as it is, and we're getting fancy today, so we're going red, even though Valentine's Day is like 5 months away. We're going to take a look at, okay, I'm in this first row, so I'm going to start at the bottom row, and in this bottom row, I can't make a choice between saying, let me choose one or the other item underneath me, because there's nothing underneath me. I'm at the bottom. If I'm sitting at any other given point, and I'm sitting at the 6, I need to ask myself, do I choose the 4 or do I choose the 1? Okay. When I'm at the 5, I say, do I choose the 1 or do I choose the 8? And it may be even easier than this, just to kind of, I've drawn it out for you here so it's aligned. So you see that these all fall in the same column, and then these align in the same column, and so do these. It's a bit harder to see with the pyramid, not the pyramid scheme, but schema. And so your bottom left item is actually in the same column as you. If we're picturing it visually in the triangle bottom left, you're in the same index, and that index is going to be C, right? So 6 and bottom left is 4. It's in the same column, but the bottom right is at C plus 1. So maybe the bottom left is at R plus 1 C, and then the bottom right is at R plus 1 C plus 1. And so again, for me at least, when I first looked at this, that wasn't immediately obvious, so I'm jotting it down in case it wasn't immediately obvious for you either. So we have this note here, and all right, so now I asked myself, okay, well, I can't do anything here. These numbers they're really, they can't go anywhere. I can't change those numbers. I can't add anything. They don't have any children, so to speak. So, okay, then I tell myself, I'm sitting right here. How do I now decide, if I'm at the 6, how do I decide whether to get the 1 or the 4? In this first step, it's obvious, and I mean, essentially, I can just say, I can tell myself, let me just choose the smaller of the two, which is fine, and that's essentially what we're going to do. So if I choose between the 4 and the 1, I'm going to say that I'm best off. I've got a minimum sum if I choose the 1. The reason I have a minimum sum is because at this point, this part of the path would be 6 plus 1 instead of 6 plus 4. So what you can do is essentially build up a cumulative path sum at every single step along the way, and once you get to the top, then you'll have actually gotten to where you need to be. You'll have that actual output that you need, which is that sum. And so in this case, I'm going to look down and look to my right and say, this one's better. So what I'll do is I'll add the 1 to the 6. I'm just going to change this to 7. So for this first implementation, I'm going to do this in place. I'll show you how to do it in place, which again, someone's going to yell at me. They always do. You run this by your interviewer, right? So when you get to your interviewer, you say there's a way to do this in place. It can save a space. You can acknowledge the fact that potentially this may be thread unsafe. So if you're running this on multiple threads, then you get a whole bunch of wacky issues. But sometimes with the context of an interview, it's like, yeah, cool, if you can do it, go mental. If not, again, we'll do it another way. But I'm going to do it like this for now. I then look at this 5. So I'm going to start iterating through this way and then upwards, okay? I look at the 5 and I ask myself, which would be a better path? Would it be the 1 or the 8? Well, the 1 is less than the 8, so I'm going to say that this is a cheaper path. And this 5 now becomes a 6, because 5 plus 1 gives us 6. I take one more step over, and this should be a 3, I believe, if I can read my own writing. That's a 3. So between the 8 and the 3, again, the 3 is lower. So I'm going to say this path, if I take this path, will cost me 10. Cumulatively, that's like from the top down, so far from what I've seen, if I take a step from here, the best I can, and go downwards, the best I can do is 7. From here, the best I can do is 6. From here, the best I can do is 10. All right? Now we take a step up. We're looking at this row now. And again, we're going to go left to right, and we're going to keep going up. Oops. I'm at 3 here. At 3, I can decide either I go to my left or I go to my right. Do I take the 7 or do I take the 6? The 6 is going to be cheaper than the 7. So I'm going to take the 6, and that's going to cost me 9. All right? Take one step over. I'm at the 4. If I'm sitting at this 4, do I take the 6 or do I take the 10? That's right, I heard you. I heard you say 10. I heard you say 6, sorry, because 6 plus 4 is now going to give us 10, okay? So not to be confused, I'm not moving this 10 up. I'm adding this 6 and this 4. Now I'm at my 2, right over here. I'm iterating and I notice, okay, well, what's better, the 9 or the 10? The 9 is cheaper, so this becomes 11. We return this number. That's how I get the minimum path to get to the bottom. All right? I hope that explanation made sense. In essence, like summa summarum, to put it all together, we're starting from the bottom, building our way up, and taking the minimum choice at every given point. So between our left and our right child, keeping a cumulative sum. and building that up, and then we'll realize kind of what our optimal scenario is at the end. So I think at this point we're actually good to go check out the code, give it a run, and make sure it works. All right. So I think actually for this one I'm not even going to need to do the error checking, but just for sake of completion I will. So I'll say if not triangle, we will return. This will return 0. All right. So what I want to do is I want to iterate through, kind of go up one row at a time from the bottom up, and do the columns from the left over to the right. And what I want to do is I want to start from this second last row, right? Not the last one. So maybe we'll say that for every row in range in the length of the triangle, okay, except we don't want to start at the last one, we want to start at the second last one, right? So we want to start at the second last one, which is going to be length of triangle -2, and we want to go up to the top, which is 0, but here we do a non-inclusive bound, as you know, so it's -1, and we're going backwards, so we'll do -1 every single time, all right? Now the column should be more straightforward, so the column is in the range of the length of the triangle at that given row, and we're just doing from left to right, so that'll be standard right there. So at any given point, I need to tell myself within triangle RC, so I'm pointing at triangle RC, I want to set it equal to, or rather I want to add to it the minimum of my left child and my right child. Again, I'm using child here very loosely, but I think you know what I'm getting at. I want to choose the minimum of triangle R plus 1, and my left child was C, right, so the one right below me, or visually to my left, and then visually to my right is one step over, so triangle R plus 1 again, and C plus 1. And that's actually going to fill itself up. That's all we got to do. At every single step of the way, that's how we add the cumulative piece. And we return triangle 0, 0, just that initial element. That's genuinely it. That's 4 lines of code, okay? And obviously barring the error checking. And again, someone's yelling at me, I know, for doing this in place. I'll show you how to do it out of place as well, but just to keep me honest and to make sure I didn't do a silly, I'm gonna do this, and there we go, super fast, super efficient. Yeah, all right? So the way that we can do this now, if we wanted to store it separately, okay? Maybe, or not maybe, but what we can do is actually recreate this cumulative effect by building up our own nested array structure that looks exactly like this. Okay, so what I can do is literally just create this thing and fill it with zeros right off the bat. So what I'm gonna say is I'll say maybe result, and so once we get to the end here, I'm gonna be returning, let's say result 0, 0, okay, and we'll change this up as we go. And I'm gonna say that result is going to be equal to, well, we're gonna do some sort of list comprehension here, and we know that we want to have a certain amount of rows. So we want a certain amount of rows, so we'll say we'll create empty arrays or empty lists for R in the range of the length of triangle. Okay, so we'll have empty arrays at every step along the way. Within them, I want to fill them to be a certain size, which is the actual length of that row. So I'll fill them with zeros to start. So I'll start with zeros for every column in the range of the length of the triangle at that given row, just like that. All right. So I know this might look a bit messy, but I hope it makes sense. And pause and kind of rewind 30 seconds if it didn't make sense, so I can re-explain it to you. But this is a simple list comprehension. I'm making R number of empty arrays, and I'm filling each of them with C zeros, just so we can match this exact structure here. What I will do though is I will take my bottom row in the result, so this one right over here, and just fill it with those default values, because they will, the cumulative amount is actually just a replica of that row itself, because there's nothing below it that can accumulate anything. So what I'm going to do is I'm going to say let's say for C in range in the length of triangle and in the last row, so at -1, what I'm going to say is this, is I'm going to say result at this index C is going to be equal to the triangle at -1 in the Cth column, if you will. So what this is going to do, this is creating, like I said, create empty result array to store cumulative path sums. And then right here, all I'm doing is fill bottom array of result array with triangle's last row, okay? So we're gonna do something really similar here. And what we're gonna do is this. I'm gonna say that now I wanna start filling this result array. So I'm gonna say that my result at RC, excuse me, I think I messed up here. I want to fill my result at the bottom. So this is going to be result of -1, excuse me, okay, because I want that last row at the bottom. So I do apologize there. I want to say result of RC, so it's going to start at this 6, is going to be equal to the value of the triangle there. So triangle at RC, so that's this value, it's going to be equal to the 6, plus the minimum of the cumulative we've seen so far. So the minimum of the cumulative, which is what we call result. And that's going to be R plus 1, C, and again, result of R plus 1, we check to the right, is going to be C plus 1. The reason I'm setting it equal, first off here, is because it's a 0. We instantiate it to 0. We want it to equal its equivalent element in the triangle, so again, the 6, plus the minimum of the cumulative we've seen so far, which is what we're storing in our cumulative, our result array, which is equal to this right now, and it'll accumulate, again, as we go, or accumulate. And so this should work as well. Again, I'm going to run it just to make sure I didn't do anything stupid. Okay, good. Now, from here, there's a way to take it one step further to optimize. Again, the optimal is obviously that in-place change, but in case you're not allowed to do that, I want to make sure you guys are still safe. So what I'm going to do here is this. We can get a bit clever here in how we track this, and the way that we do that is by realizing that we only really need one row at a time. We don't actually need this entire result array. And let me know in the comments down below if there's an even better way to do this in O event space, because I didn't know it off the top of my head, and I would like to learn, but this next one will definitely be a lot more efficient. And what we're going to do is, so we can actually do this in just one straight array. And what I'm going to do is I'm just going to recreate the bottom array, or the bottom list that we have here. So this 4, 1, 8, 3, and then start accumulating by replacing the values, kind of like how we did in our initial in-place change, except now I'm going to do it just one row at a time and build it upward. And you'll see what I mean. I would pay attention to this one because this one's clever, and tricks like this have been used in other problems, so I think you can definitely take this with you in further questions. So in here, I want to fill it with numbers, and the numbers I want to fill them with is for every num well, excuse me, sorry, I'm blanking out here. In triangle of -1. So for every num in the bottom row, I want to put that into my result. That's going to be my cumulative piece so far. All right, and what we'll do is, this is no longer going to be like this. You know what? I'm probably confusing you guys by just changing things around. So let me not be lazy, and let me just keep what we need. Okay, so we've got this original loop. I think this will make sense. All I'm doing is I'm recreating this bottom row over here. Now, how do I actually go about saying to myself, okay, what's my next best cumulative step up? Imagine I had the following, and maybe as I do this, I'll track result. Okay, so result is equal to 4, 1, 8, 3. Okay. What I'm going to do is, I want to eventually, this is going to be my spot where I'm going to actually have my final result that I want to return. And the way I want to do that is this. In this position, I'm going to keep my leftmost next kind of optimal accumulation point. And so basically what I'm going to say is, I'm going to say that result at the column that we're comparing it to, because it goes from left to right, and they shrink. So we're always going to have that column space. We're going to say that the result at that column is going to be equal to, or rather, we're going to add to it. So right now it's a 4. What we're going to want it to be, no, excuse me. We're going to want it to be this. We're going to want it to be 6 plus the minimum of these two. Well, how do we get the 6? The 6 is equal to triangle at RC, right? Okay. And then the triangle at RC, we want to add one of these two. Both of these two are already in here though. So we want to add to the minimum of result C and result C plus 1. What's going to happen is this. Let's walk through it. I want to make sure that you guys really understand this. And this is going to be result of 0 at the end. If I do that, triangle RC is 6. We're going to say 6 plus the minimum of these two numbers. That's going to be the minimum of 4 and 1. So that'll give us 10. It's going to become a 10. All right. Wow, that's going to become a 7. The minimum of 1 and 4 is 1, kids. It's not 4. I take one more step over. I'm at the 5 now. 5 I want to change to the minimum of 5 and 1 and 8. Or rather, sorry, I'm at 1 right now. In my triangle, I'm at 5. I want this to become the minimum of 1 and 8 plus the 5. So we'll take the 5 plus the minimum of 1 and 8, which is 1. That'll give us 6. All right. One more step over. We're at triangle 7 and spot 8 here in our result. We want this spot to become 7 plus the minimum of 8 and 3, which are right here. All right. So that'll be 7 plus 3. That'll give us 10. Does this look familiar? 7, 6, 10 is this right here. Is this piece right over here, 7, 6, 10. We started with this bottom row, and we made it 7, 6, 10. If we repeat this 3 here now has become irrelevant. If we repeat this process again, you'll see very quickly, and I do urge you to try this. This is going to become 9. It's going to become 10. 9 and 10. We do this one more time. This becomes 11, and we're done. We end up returning that first element, and that's how you do it in that linear space. So finally, again, I'm going to run this, make sure I didn't make any mistakes. Honest to God, like this is 3 implementations, none of them had a mistake, man. I got a horseshoe up my you-know-what today. Yeah, so I really hope you guys learned something here. I know it's like we're just around 21 minutes, I think, right now. It's a bit of a longer video, but it does give you a walkthrough of quite a handful of solutions. I really hope you enjoyed this. Let me know if you had any questions. Let me know what you want me to answer next. Don't forget to subscribe. Don't forget to like. Don't forget to share. Okay, with your pets, with your friends. I always say with your grandmother, with your estranged aunt who you're not speaking with anymore, but you should, because she would benefit from Baby Bear 4812 as well. Okay, so make sure that she sees this and that she subscribes and shares with her friends. All right, I'm done. I promise. Peace. See you guys next time.